Hi, I'm Seung Lee, and today's topic is about learning the real function for a misspecified model by Eric Talvisier, ICML 2018. Contents are following. First, introduction, and next one is background, theorems, algorithms, and experiments and results, and the final one is discussion. First, introduction. Problem is that when the dynamic model flawed, like it has some wrong information, typical RL algorithm like model-based reinforcement learning or data aggregation fails catastrophically. So the paper suggests algorithm that first one is dagger MC and the H dagger MC. It means dagger means data aggregation, and MC means Monte Carlo, and H means hallucinated. I will explain it later in details. The paper gives first theorems about error bound for planning performance, and second one is bound above error by error in dynamics model, which means the performance of the error uh, error of the performance is bounded by the error in dynamics model. So also it gives the more tight version of the error bound. Second one is experiment with a simple game. It gives best result in among the other algorithms. Second, background. First, RL. The when we define RL and following problems, uh, the agent is defined and the environment and the reward and action states and so on. So in summary, an agent interacts with an environment and receiving some reward along the way that indicate the quality of its decisions. So its object is following: find optimal policy pi, maximize some value function and its expectation. Model-based RL is briefly learn initial policy and the collect samples, and with it update policy and dynamic models, and also we can learn the real function. The problem is following: if the model is flawed, it can fail. Typically, it can fail, or it can huge fail, because error will become bigger and bigger in step by step. Dagger is the method that update the policy to mimic the expert policy. I will explain the next slide about the dagger. For dagger, first we initialize D, which is the data set of the agent, and the initialize policy to any policy in policy space, possible policy space, and for end step, uh, we let the pi I is a linear combination of the expert policy and the our policy, initialized policy, and the sample t-step trajectories using the pi I, and get dataset of visit state by the pi I and the actions given by experts. and aggregate dataset with D and union of DI and update D and the train classifier of the next pi I plus 1 hat on D and for we take best pi I hat on validation set. Uh, the paper used an example shooter. It is a game introduced by the Talvivier, a previous paper 2015, and the shooter domain is following. A is the initial screen and the B is the when shooter shooter is consists of the shooter, the spaceship, and the bullet and the targets. Three targets and the many bullets can shoot by the spaceship, but when the one bullet will shoot, uh, it get -1 reward. So we -1 reward, and the uh, when target is hit by the left of the target, it get 10 reward. Also, we hit the bullseye. We can get reward 20. It is simple in this case, but it can be complex by the moving bullseye or the moving the targets or and so on. So it made flawed model, which is the which is dynamic model is factored MDP, and the next pixel of the screen is determined by the environment or neighborhood of the pixel. So when the information is not in the neighborhood, it cannot update correctly. So it gives some error to the states, and we cannot define the reward because when we have that shape means the target is bullet hits target. When the bullet hits target, this shape is shown. So this shape we cannot define the reward function. Also, it seems easy to human, but in the RL agent, we should analyze it pixel by pixel, so it is hard or complex problem to the RL agent. Hallucinated replay. It is a H of the H dagger MC. When the RL agent is sampled from the environment S1 and A1 and S2 and at A3 or A2 and S3 and so on. Training example is for S4 is given by the S3 and A3, but in this case we sample from the environment and our model or the any model, and we have some hallucinated states, and sometimes we update S4 from the Z3 hallucinated state and the action of the environment sample when we update Z3 to the S4. When we use it, we will shrink some errors from the misspecified model, like this one. Another background is about terms. D is a distribution of the state and action obtained after T steps, and the Q is the T step action value of policy pi, and the value is the T step state value of policy, and the P head and R head, D head and Q head is a set of the not this set, sorry, model of the model our model of the dynamics model and real distribution action value function. Also, concepts are defined the a rule out algorithm. For every state action pair S and A, the planner executes n of T step samples rule out using P head, our model, starting at S and taking action A from the P, and following rollout policy is low. For each step in individual rollout, R can give reward. It is also our model. So rollout algorithm is just a sampling from the P head and RL. Also, I will introduce about the theorems and lemmas. First, we can define some validation error of the uh, true Q value of the pi is our or any pi, and the our data from the data we can get state action values, and the true state action value of when the policy is given by pi in the T step. So this is the definition. So by the lemma 1, it is given in previous 12 work. So I also the all the theorems can will not uh, proved will not proved by me, because proof process is not important, so I will skip it. Sorry for the skipping. And first lemma is the let Q be the value function returned by the applying depth T or of Monte Carlo sampling to the model with rollout policy. Rollout policy means the expert policy or our goal policy of of our goal policy, and the pi is given by from the Gridley Q bar is the action value function from the data trajectories. So for policy, any policy pi and state distribution, we can bound this value, which is important for get some optimal policy, is bounded by the this error and the Monte Carlo error. This is from the stochastic of the Monte Carlo sampling, so we can omit it, and this one is important. So we can bound this error by this error. So first lemma is the its meaning. So next one is the bounds this error, uh, state action error by the uh, model, dynamics model. It is our problem. Problems bound this model error and the state action error. And the for special case, we can get some tight bound. So tight bound gives better results in the algorithm. So in theorem 3, we give some tight bound in this form. The distribution of the from the state action distribution and the blind policy. Blind means it is conditionally independent of the current state given the history of actions. So when the policy is blind, we can get some tight bound. Also, uh, this is another case of the error bound. When we have some reward error, it is bound. The the control performance is bounded by the reward error and previous error terms, like this one. Also, we can define ht eta law. It is from this part. We can define the joint probability of the S2 and Z2, which is given in this form, and S1 from the eta psi, from the psi we can get S, and from the law we can get Z. So this is defined from the first we start with the S1 and A1 when this one, and from the S1, and we split the two states. So we can define this form. The expectation of the psi and the from t from the for the t state st and zt at, we sum of these policies and the probability because we have joint distribution. So when define it, we can shrink this term to the only lever term, and the theorem 6 gives the tight bound for the tight bound and representative bound. We have each value, all the value, so its error is bound, and we can get optimal policy in the between the error and the true value. Algorithm is following dagger for model-based RL. Is first we have some exploration, distribution, and numbers of iterations and number of samples per iteration m, and the online learner and planner. uh, we can get initial data set D1 and the from the D1, and we we have some online learner, and the result is given in P hat. P1 hat is initial model, and the from the P1 hat we have policy P1 pi 1 and some for n iteration, and the uh, per sample we have uh, sorry, number per iteration we have number of sample m samples, and so in the probability of 0.5 we reset using mu, and the using mu we reset the distribution sorry, we reset the SNA from the use pi n minus 1 and the distribution fixed distribution, or reset the SNA from the exploration distribution and take action A to obtain S prime and add dn to the this value to add dataset, add to dataset, and from the online learner and p hat and minus 1 and dn previous and now dataset, we update dynamic models, dynamics model and the policy, and we have the sequence of the policy. And hallucinated dagger MC is consists of this part. It is complex, but it is consists of two big parts. First one is a sample from the eta, sorry, psi, and the sample and rollout, parallel rollout. First from the environment and the model to rollout. Sorry. Not two. One rollout consists of two paths, and the t minus 1 the length of the t rollout. With sample and parallel rollouts, we update dynamic models and the real and the planar MC planar. So by this procedure, we can pseudo define some when the state in the misspecified states, we can define these terms. So experiment and the result is given by six pictures, and first one is using dagger MC only, first law, and the second law is H dagger MC, and the column is means when the model limitation it doesn't have any model limitations, and moving both sides, it means both sides can move left and right. So when the both sides located in the center, we cannot know the next move from it, because we cannot know when the first order, when we use first order Markov chain. It this state, center state, uh, we cannot know it is from the right or left, uh, right or left, sorry. Also use limited model 5 by 7 neighborhood. So the sorry it is shown the dagger MC algorithm to the policy update, and the H dagger MC to the policy update, and the this hallucinated and standard perfect means to the this method to the reward updating. So in every case, the H dagger MC apply H dagger MC to the policy, and the reward is gives the best result in the in in this in each column, and the for each picture the H dagger MC apply the hallucinated version of the reward. Reward model is trained on the hallucinated states is gives best result. So in summary, the paper suggests new algorithm H dagger MC. It serves tight error bound for the value function optimal between optimal and hours, or not the optimal. Any policy and the hour policy is given bounded by this value, and this value is bounded by the other physics model, sorry, dynamics model, and the apply this algorithm to the example shooter and check it that check that it gives best result. Thank you for listening, and any question?